How is everyone doing? It's like enjoying the conference. It's just super nice to be back in San Francisco. It's really gorgeous here, and the gorgeous sunset yesterday. We're walking around outside. Anyways, welcome to Akka in Production. We'll be talking. First, I want to apologize a little bit if the slides might be really slow for some reason. I haven't done a presentation Keynote in a while, and Apple's new Keynote is like really, really slow for some reason. I'm principal engineer at Socrata. I'll tell you a little bit about what we do. I've done Akka and Scala projects for a while, for a number of years. In fact, Akka was kind of the gateway drug for me into Scala, which was one of the projects that got really excited since the beginning. And here to share with you some of the what gets me excited. Just a few plugs. If you are interested in columnar databases or extremely fast serialization, you can come and talk to me later. This doesn't really have to do with what I'm going to talk about, but it's just some interesting stuff I'm working on, which didn't make it into submissions for conferences like this. So, who is Socrata? I'm very happy to represent Socrata. We are a Seattle-based company that basically democratizes public open data. You can think of, for example, the city of San Francisco as our customer. They have really interesting data sets on how they spend your money as someone who lives here, and on 311 data, 911 data. In the past, governments would basically put them up as Excel files on their website, and you might have to fill out a form to download it. And what we are transforming that into a really nice UI that anyone can go look at and analyze and get really useful information, as well as APIs for developers to build apps on top of. So this is a public open data that consumers as well as apps use. And we are the leading open data platform with a whole bunch of, with a whole bunch of governments. And just a really quick story, we started with a monolithic Java app, and a few years ago started migrating this more and more features into Scala. We started at Scala 2.8, which feels like ages ago. And back when we started, there were very few libraries available for Scala. So we had to, we wrote our own JSON parsing and HTTP library and this kind of thing. And nowadays there's like so many choices that you spend a lot of time even picking through choices. But to the meat of the talk, now there's a lot of use of this word reactive, right? Everyone wants to build reactive applications that are event-driven, scalable, and rooted in all this, right? So what does that really mean, right? And for a lot of people, this means frameworks like Akka, which helps a lot in terms of building message passing architectures. And we'll look at some examples that went through mostly at my previous company, but I'll tell you about experience in terms of architecture, and we'll talk and of course play is based on Akka. And we'll go into a lot of things about putting Akka systems in production and various things that you need to watch out for. And you can see that Akka is being used at a lot of companies, and not just companies in terms of individual applications, but you can see that it is starting to be used in a lot of frameworks as well. Like Spark uses Akka, some Akka underneath the hood. You guys might have heard of Gatling, which is that logo with the Gatling gun, which is a really awesome load testing tool written in Akka, using the nature of Akka to fire off a lot of requests at once. So a lot of really interesting projects. We'll skip over agenda really quickly, but among the things we'll go into in a little bit includes back pressure and monitoring and a few things like that. So I'm going to talk about ingestion architectures with Akka, how, a few things. One of the really good scenarios that Akka is good at is for writing streaming applications. So I'll just go into this really quickly. What some, kind of like the standard Akka stack that we've been using for a number of years, using Spray as the high-performance HTTP front end, and various packages that you're probably familiar with, including SLF4J, Yammer metrics, which has been renamed a couple of times, is now like CodaHail metrics or Job Wizard IO metrics. At the time we started, Spray was the only HTTP, was basically the only one that had really good Akka integration. Now a lot of HTTP frameworks, Socrata and a few others, have good Akka integration. So here's a problem statement. Let's say that you are building a service to ingest analytics pings from video players, so that every time a consumer goes and watches video on the web, on the browser or on the mobile phone, it sends like analytics messages. And so an architecture for doing this, maybe the raw pings or HTTP pings, they would go into Nginx. And from Nginx, maybe you feed this, you need a way to get the logs and feed them into a message queue. Nowadays, a lot of people use Kafka, so let's say that you use Apache Kafka. Then you need to get these message pings out and analyze them and store them and transform it. So you need something to plug in there to transform these pings. We'll talk about various pieces and how you can use Akka in them. These are things that I've built and put into production multiple times. So the first thing that we wrote was something called liblocksd. This is a Kafka file tailer which uses Akka underneath the hood for concurrency. So when you get these log files, you can imagine that what Nginx does is it's going to write these log files. Then when it gets to a certain size, or more likely at a certain time interval, it's going to rotate the logs. And when you rotate the logs, it actually moves the files to a different place. So the file handle doesn't change, but the file name might change. And so one way we map this is that you can map one actor per file handle. So let's say that you assign the current file gets one file reader actor. And as it gets moved, even though it is moved, that actor can stay with the file so that it can finish off ingesting the last bits of that file before. And at the same time, the new file is being written, so you can assign a new actor to it, and it starts reading. And you can have a little bit of concurrency there that happens. Another scenario why you might want the concurrency is because let's say that you have a failure. You might want to remember, you might want to write off checkpoints and remember where you left off reading. And so you might want to play catch up. At the same time, while you're catching up, you still want to ingest the latest logs. So you can have that going. So you can have an actor for the new files and an actor for replaying old logs. Those all go concurrently to a Kafka feeder, which goes off to a Kafka. In those days, Kafka was just starting to have an async API. So nowadays, those actors don't have to feed into the Kafka feeder anymore. They can go directly into the Kafka async producer. But back then, they didn't have that. So this is really simple. Don't need to talk too much about it. After you feed into the Kafka, you need to process it. And at that time, when we were starting this, Apache Storm had just come out, and that was the latest and greatest thing, right? So everyone was trying to write stuff using Storm, so we did too. So I don't know how many folks are familiar with Storm. Feel like it is. I guess you hear about it less and less these days. You can actually. So the way Storm works is that there are spouts and bolts. And the bolts are actually where the computation happens. They're designed to run on one node with threads. Turns out that you can use actors. This is an uncommon use case, but you can use actors even within bolts, like within frameworks that typically relegate your code to a single thread. And that way you get some concurrency. You don't have to do this. You don't really need actors because the way that Storm works is you're supposed to define functionality in bolts, and they're supposed to pass messages to one another. But one reason why you might want to do that is because you might want to have code that is co-located on the same node, and you want to guarantee that, which is what we were doing. And when bolts fail, if they come back up, you might want that functionality to come back up together. It depends on your application. It turns out that what we found was that Storm was very complex to run and troubleshoot in production. It has a lot of moving parts. It has a central agent that coordinates stuff. It has supervisors, and it has workers, and it has zookeeper. So we found that a whole bunch of production incidents that at 2 a.m. Folks that were on call wouldn't know, like it became difficult for them to track down. Okay, where's the problem happening? Like there's a lot of log files, and they didn't know what to restart. So it became kind of difficult to troubleshoot. So after that experience with Storm, we wanted to try some new things to look at, can we have a system that is simpler to run in production? So we experimented with Akka cluster when it first came out. So in this scenario, you have Kafka consumers. They talk to a service which has a spray endpoint, HTTP service. And what we do is that we would do a cluster-wide grouping kind of thing, where we would have a cluster router that can route messages to the right processing, and would have some state in each processing actor. So we want to send messages across the wire like that. So this looks like a nice diagram. It was really cool to write the code for. This was still like a bit too complex. I think folks were afraid of getting paged for this system. There was still a lot of crosstalk in the network, and at that time the Akka cluster had just come out and it was not stable yet. So it was difficult to get visibility into like nodes would go down and weren't sure why they would go down. Since then it's stabilized a lot. So by no means don't get out of this talk that you shouldn't use Akka cluster. The other thing was that by mixing the HTTP and Akka paradigms, HTTP is request response, and Akka is very much a send messages one way. It became hard to debug because mixing the two paradigms. And most of our developers, a lot of them were new to Scala. They found that actors were easier to understand than futures. That just happens to be our experience. That maybe it maps very well to the object-oriented world. So what we ended up doing is we ended up simplifying this ingestion pipeline quite a bit. We basically used Kafka to partition messages. So we made the log tailor smarter and able to send messages to the right Kafka partition. So Kafka is used for shuffling data. Then you have a really simple single process that consumes from each Kafka partition. And that single process contains actors that are all local. So this is extremely simple architecture. It's really easy to understand. And we ran it in production, and it was very easy to gain and just keeps running. So we finally had a system that we're happy with. I guess the overall lesson is that I think a lot of these technologies, the Akka cluster is really cool, but you have to make sure you understand when to use them. Like you want to use the simplest solution that is possible. If you don't, I forgot who said this, but the first rule of distributed systems is don't distribute, right? So now I'm going to go into a little bit of code, since this is a Scala conference after all, right? I'm going to talk about something called stackable actor traits, and this will lead into talking about monitoring and things like that. So this is a pattern that I call stackable traits. The things that you need to repeatedly do for every actor that you have. You need to monitor it, you need to log it, you need to do metrics. There's a lot of code that gets like repeated again and again, right? So let's say that we want to wrap the receive block with some kind of logging. In this case, it's a print, but it could be like logging or anything else. So how can we make this easier and easier on the eyes and easier on the code? So let's define a trait that we call actor stack. So what this is going to do is we're going to shift the main functionality of an actor from the receive method to something called wrap the receive. And what the receive is going to do is going to basically redirect this. So by implementing an actor stack, you can basically wrap your receive with various kinds of functionality. And you'll see some example of this. How many people know what a partial function is? Okay, that virtually everyone. Awesome. So you can chain partial functions. You can do basically wrap receive or else unhandled, and that gives you a new partial function. And unhandled is the default handler for messages that don't get handled by receive. So as an example, I can have two instrumentation traits, and they can be mixed, and the order that you mix them will determine what behavior gets executed first. So, for example, I'm going to have an actor that extends actor with instrument 1 with instrument 2, and then you can see like the certain order that this stuff gets executed. This will make a little bit more sense when you see like real examples of how this is used. Okay, so in terms of productionizing Akka, it's said that the distributed systems, the only thing that really matters is visibility. I think this is like, definitely true. And one of the constant themes, I think, productionizing is how can you get enough visibility into your Akka system? So the first thing is performance metrics. What we did was we added a trait that adds standard kind of performance metrics for every actor. How frequently your message is handled, how much time is spent in the receive block. And the metrics all get exposed through Yammer metrics as well as through an HTTP route so that you can query, we can have an agent that queries and forwards that data on to StatsD or Graphite or your favorite aggregation thing. It's named the metric C route. Getting the mailbox size is hard. It's actually impossible now because a long time ago there used to be an API that allows you to get the message size. You can no longer get the mailbox size unless you implement a custom mailbox. So you would have a stackable trait that looks like this. So it's called actor metrics. And so you define a receive timer and basically time this block. The metrics timer does both frequency as well as duration. And you might see graphs like this. This is from Datadog. What you see here is the 95th percentile processing duration for the actors in this pipeline. And you can see there's 3 of them. And so by looking at this, you can kind of, if you correlate this with something else, you can figure out where the slowdown in your system is. There's a little bit of a trick depending on how you do your feedback or back pressure, which I'll talk about in a sec. But here's an example of correlating this with across the board. That's a little bit hard to see, but it basically corresponds to so this is basically broken down by hosts, graphing the latency across hosts, and you can kind of see like that there's some unevenness across the cluster. There's certain nodes that are slower than others. The other thing that is nice to graph is, it's a little bit hard to see from here, but is the message handling rate. If I amplify this a little bit, this lower portion, it tells me, like what I look for is when one actor slows down relative to others, that often tells me that that gives me another clue as to where the slowdown in the distributed system is. If the first stage slows down a lot, then you would see a bigger divergence in those lines. If everything lines up perfectly, that means that everything is flowing at the same rate, which is what you would expect normally. But there's always some variation. I'll go into this a little bit more, but there's some multiple ways of slowing down your system with doing back pressure. If everything is local, then you can use what is called the bounded mailbox, which slows down your messages that get pushed to the next actor. And what you'll see if you performance profile it is that you will see that a significant portion of time is spent enqueuing in this bounded message enqueue method, which is spent waiting to push data, which is a sign that this back pressure is working. What would be really cool is so you guys know VisualVM has a wonderful graph for showing threads that the thread graph is kind of useless for Akka because you have so many different actors that are interleaved onto threads. So what would be really cool is haven't had time to do this, but it's a VisualVM plugin that actually shows you how that correlates which actors are running on which threads, or actually just shows the actor execution graph, which would be very cool. So let me know if you're a VisualVM expert. I'm sorry? Oh yes, someone said that you could print out the thread name. Yes, that's definitely something that you can do. I didn't show. I moved the slide for this later, but you can use the MDC. In fact, if you use Akka's logging facility, it does this for you. Is that it will put the Akka actor name in the SLF4J MDC context. Then when you get it in your logging, which is you can definitely do that. That helps a little bit. So one thing that we're used to as Java Scala developers is the stack trace. Stack traces are really friendly and helpful when we do standard threaded programming. The problem is that if you do stack traces with Akka applications, you get something that looks like this on top. You get all the stack trace up until the last time that the message is invoked or the actor is invoked. Then you're going to get a bunch of stuff about Akka dispatch, future, and things like that. So this is unfortunately not terribly useful. I think that what we really want in the Akka world is the Akka equivalent of the stack trace, right? You want something that tells you, okay, I got a message from, basically a message history. And I have this actor that sent this class of message and so forth, right? This is something that you would really want for Akka development. And so this is where getting tracing comes in. If you had this kind of data, you might be able to do something like this. I'm sorry you can't see the words very well. They don't really matter anyway, but what you see here is it's called a Sankey diagram visualization of trace data that we have. And like the direct lines are basically where one actor sends a message to one other actor. The more complex thing in the middle is where you have one actor that is sending data to multiple places, and that kind of flows. This is, by the way, for one of my projects, which is the Spark job server, which is written in Akka. And you have one actor that's flowing data to different places. So this you can also enable through the actor stacked trait pattern. So what we do is that we have a a partial function called a message Id Extractor. And what this is designed to do is to extract you want to assign a message ID to each flow of the messages. It's how you implement tracing. So that's something that you would implement for different classes of messages. And then we wrap the receive block around something that every time you get a message, we're going to extract out the ID and send it to a collector. And the collector will get an edge which has the sender ID as well as yourself, as well as the message ID. And this will let you then do basically send one edge of the graph. And then you collect enough of these edges, then you can start plotting fancy things like the Sankey diagram. Essentially, this is how things like Twitter's Zipkin and other distributed tracing things work. There is now an open source project that does exactly this, by the way, so I'll point this out in a sec. So Akka Service Discovery. This is something that is definitely needed if you're doing Akka cluster or Akka remote across multiple nodes. For Akka remote, you need to know where those other nodes are. If you're using Akka cluster, so Akka cluster, in theory, it knows about all the other nodes. But the thing is, in order to start an Akka cluster, you actually need to know 2 seed nodes. So how do you know the seed nodes? This is similar to any kind of peer-to-peer system has the same problem, that you need to discover the first nodes. Like Cassandra, if you work with Cassandra, you have the same problem that if you use fixed seed nodes, then eventually those might move and you'll have errors in your application. So you can use Zookeeper or something like etcd to register your seed nodes for Akka cluster, or in the case of Akka remote, you can just register all your nodes that way. There are multiple projects that are trying to do this. I know of one which is the Akka cluster inventory extension that sounds promising. I'll just have a note about Akka. If you guys work with Akka remote, you guys probably all know this, but Akka is very finicky about IP addresses. You have to be very exact, even for local hosts. It sometimes matters whether it is localhost or 0000 or 127.0.0.1. I'm not exactly sure why it is, but it is very finicky. If I turn on VPN on my network, then Akka test will no longer work. So if you're working with especially AWS or Docker and things like that, you have to be, just make sure you test the heck out of the IP address discovery. Yeah, so the question was, are we running on the cloud infrastructure? Yeah, I think right now we are, or for our new infrastructure, we're in the transition. We're migrating to running in AWS with Mesos, with Docker. So this is something we're still trying to figure out exactly what strategy for the IP address discovery stuff. We use Zookeeper in production, but we are investigating etcd. So I think it's still it's still very much fluid right now. Yeah. Here's some good links, useful links for you guys. The first project I'll plug is called Kmon.io. You guys might have heard of it. It stands for Akka Monitoring. These guys, this uses a different approach. It uses AspectJ to weave in the instrumentation, including some tracing stuff. By the way, the actor stack trait stuff I talked about is also open source, but you get a link for that later. And this has backends such as StatsD and Graphite, and this is an easy way to get started because you don't have to. If you already have Akka actors, you can just include this project, and it will weave your bytecode and forward stuff. The other one that looks really interesting is called Aqua Tracing. This is something that I'm planning to try out in multiple my own projects, which is for tracing Akka invocations and writing it to Twitter Zipkin for visualization. So now we come to a very interesting topic about back pressure and reliability. right? So I'm thinking you guys probably, if you're in this talk, I probably don't need to mention why you need this, but back pressure is the ability to tell senders to slow or stop down, And if you keep sending messages to an actor, by default, what do you think happens? Right? Like by default, that's the next slide. But it's not enough to look at individual components, because I've heard some arguments that, well, why do we need back pressure? Because TCP has back pressure, right? But that's true for one connection. But if you have a lot of connections, you have to make sure that the whole system can slow down, which is what we're concerned with. So by default, actor mailboxes are unbounded if you don't change the configuration at all. So what happens when one actor writes to another and the rates are different, say the publisher is a lot faster than the consumer, is that your mailbox will start eating up all of memory. And it's pretty easy to verify. I'm actually find it kind of curious why that's the default, is to use unbounded. But one strategy is for using bounded mailboxes. If all of your so what happens with bounded mailboxes, when the mailbox is full, messages go to dead letters. You can then watch for dead letters and see if messages are overflowing. And there's a setting called mailbox push timeout time that tells it how long to wait when the mailbox is full. And what happens if it waits and the timeout occurs, then the letter goes to dead letters. However, this doesn't work for distributed systems. A remote node has no way of knowing that the other mailbox is bounded. So what the common wisdom is to use real flow control, which is a lot harder because you need to implement a protocol. Push, pull, acknowledgement. There's multiple patterns for this, and this works anywhere, but it's more work. We'll talk a lot more about this. So just to show you a graph, because we love graphs, a working back pressure system causes the rate of all the components to come in sync. So if you look at this graph, you notice that you have a publisher and a subscriber. Well, actually, the publisher is actually a Kafka consumer actor. So this is pulling messages from Kafka and writing it to a consumer. The purple line at the very top is the Kafka one. It's when we turn it on, and the step function is when we turn on the Kafka, or pulling from Kafka. It starts out very, very high because it's trying to push a lot of messages. The other guy, the consumer, is slowly ramping up, and over time they come into agreement and the graph lines up. You guys have probably heard about Akka streams. This is the new implementation based on reactive streams. I pulled the graphic from the website. But the way that Akka stream works as a protocol is that the downstream actors are going to signal upstream about demand. So it's going to tell it, okay, I have more work. And then the upstream guys are going to send work down, which is what I call very conservative, because the upstream folks, the protocol is that it's not going to send any data unless it actually knows that there's work to do. This works very well when your topology is a straight shot line like this, or if your topology is fan out, where you know what workers you have, or it's very, very stable. How does this work for a fan-in scenario? For example, let's say that I have multiple input streams. This might go to a resource like a database. They might come and go. And so I do want pressure for these streams, but it's no longer a stable system. One note about the way Akka streams works is that Akka streams is based on, you define a flow diagram using a DSL syntax, which is actually very cool. And then once you define it, then you materialize it. And the materialization step will create the actors and create a flow. The result of that, though, is that it works very well when your topology is static, right? But in this case, it's not static. So here's one way that back pressure could work for a fan-in scenario. Let's say that you have this new stream. What it does is it sends a registration message to the writer. and the writer will send back the same kind of Akka stream style pull request, which is I'm ready for data. Then the data gets sent. So this is a simple model, and it has the positives is that you can easily control the number of clients. So that if a new guy comes in and requests registers, and the guy's overloaded, then it might not hear back. But it does have high overhead, because if you have a lot of streams coming and going, now the writer has to keep track of who are the clients. And let's say that it says it's ready for more data. Now it needs to think about how many clients there are, and might need to send out these ready for data messages to a lot of actors. So there's a lot more management that happens in this model. I'm going to come back to this because I have an idea about how to address this problem. The other problem that you might want is at least once delivery, right? What if you can't drop messages? Which is true for various scenarios. So let's say that you assign a unique message to every ID, a unique ID to every message. So I send message 100 and message 101, and I'm just going to acknowledge every single message with an ACK. So I get back ACK 100, I send message 102, and then ACK 101 doesn't make it. All right, so what happens? So what I do is that I'm going to have an ACK timeout, which can implement using the Akka scheduler. And I'm going to start resending messages from the last time, the message after the last acknowledged message, which is, in this case, 101. So resending messages requires keeping the message history around, unless you have a way to persist it, or you use something like Kafka where you can replay messages. Right, so you can use Akka persistence, which has this kind of persistence. It writes the journal to disk or to Cassandra, etc., and it marks every message whether it's been sent or seen before. So it's able to go back and replay messages, and it has an option of doing it exactly once, where because it can mark every message, it can see whether it needs to resend a message or not. So I'm going to tie these two things together, back pressure at least once. So these are, in theory, two separate concerns. You have the need to back pressure, and you have the need to do it at least once. Here's an idea for this is being implemented in one project. What if you could combine it to have an efficient protocol that has both? So the way that this works is, instead of waiting for the consumer, the writer, to tell it that it's ready, I'm going to have a slightly more optimistic approach. I'm going to assume that my publisher can send a message. But that publisher is going to watch the ACKs. And what I'm going to do is I'm going to have an upper limit of unacked messages. So let's say that the upper limit is 10. Then if I send message 100 and I send message 110 and I still haven't gotten acknowledgement of message 100, I'm going to stop. So this way, I'm combining a way of throttling the publisher along with a way of getting acknowledgement and knowing when that stops. So this is one pattern that could work much better for fan-in scenarios. You combine this with the rejection message from the writer, from the consumer, that lets it control the number of clients that can connect. Finally, the other thing that you want to do in back pressure is to think about futures. This is another common pattern, is that you might want to limit the number of outstanding futures. That a lot of databases now, like say Cassandra, supports asynchronous APIs, and in Scala those will be expressed using futures. So you do have to deal with futures at some point. So this is one pattern that basically every time I send a future out, I'm going to increase a counter. And when I get back, I'm going to check to see if I have too many outstanding futures, in which case I'm going to send a rejection message, too many outstanding futures. And when the message future is completed, it's going to go and decrement that counter. I'm sorry? Okay, yeah, so I heard someone say you can use a dedicated thread pool. So you can use a thread pool, but that doesn't prevent futures from piling up. because futures are mapped onto thread pools, so you'll still end up having a lot of accumulated futures, which essentially eat up all of your memory. Just some simple patterns for Akka developments. The way that an actor fails is different when the actor class constructor runs versus when it's processing messages. At least the default failure strategy is. So that's something you want to be aware of, is what kind of code do I have when I initialize? Like you might want to have an initialized message that instead of putting all your code in the constructor, because by default, if the actor class dies in the constructor, it won't get restarted. If you want the default behavior of I process a message and it restarts automatically, then you want to use a different paradigm to use an initialized message. And another thing is learn Akka Test Kit. This is a really, really good testing framework for testing messages and message expectations. It works really well. They even have a mode that works, that simulates a distributed environment that spins up multiple JVMs that talk to each other, which is extremely cool. There's a lot of examples in the Spark job server repo if you guys are interested. And there's a few other things for gracefully stopping your actors when you run the tests. I think, wait a minute. Oh, yeah, so unfortunately I don't have the exact links here, but if the slides will be published, then you guys will be able to see the links there. But there's the code for actor stack is actually open source. It's part of the Spark job server repo, and you guys can check that out. Thank you very much. We'd be happy to take questions. I've been asked to have folks come up to the speaker so that the kind folks recording the slideshow can get the question.
I'm just curious if you're...
So do you mind walking down? Thanks. Yeah. Yeah, thanks.
In your case, how are you consuming the data from these governments? Like, say you set up a deal with City of San Francisco. How do they send you their data? Do they hit one of your endpoints, or do they have? How do you consume the data that they're giving you from all the various sources?
Oh, it really varies a lot. I mean, it's anything from you have to set up an endpoint for them, which they post data to they use one of our tools to upload data regularly, like every day. There's different ways, but we have public APIs to let people upload data regularly. Yeah.
What's been your experience with using routing for actors? Stay away from them, or?
Oh, routing actors?
Yeah, for pools, managing pools of actors.
Oh, yeah. So, I think you're talking about a standard Akka router functionality, right? In general, they work pretty well. I think that, especially if you're talking about the local case, they work, they work pretty flawlessly. But if you want to implement a distributed router, then you have more things to watch out for. And there's a couple routers that work for the local case but don't work for the remote case, so you just have to watch out for that. Like, there's some work sharing ones that has to know about the state of the mailboxes. And in a remote case, you can't find out the state of a mailbox. So it's more limited. All right, well, thank you very much. Yeah.